Here we are going to talk about the types of spatial database management system. So as you can imagine, the spatial database management system is kind of like the standard database management systems plus some spatial attributes and also some spatial operations. So yeah, one way to view it is kind of like the standard DBMS. You can plus some spatial subsystem, and that spatial subsystem it needs to support the data types for the spatial data, for the spatial geospatial data, and also some operations, some functions for the geospatial data, and also some indexes for the geospatial data. So to realize the spatial database management systems, they are different ways to realize it. And they, in general, they are three ways, the three types or three ways. The first is the RDBMS based approach. So this one is by using the relational database management system to build the spatial database management system. And the second type is the loosely coupled approach, which means that you separate the general DBMS from the system that handles the spatial data. So it becomes the loosely coupled approach. And finally, is then integrated approach, which directly includes the spatial data management and spatial data operations and also spatial indexes into the DBMS system, and then it becomes one integrated approach. So first of all, let's talk about the RDBMS-based spatial DBMS system. So basically, that means the fundamental DBMS system is the relational database management system, and then it doesn't really has the data type of the geospatial data, and it doesn't really have the operations for the geospatial data queries. So in this case, it's usually using relations, or you can say tables, to store spatial properties. For example, like in this example, the first table that we could have is the country, and in this country table we have the name of the country, the capital of the country, the population of the country, and then you can see that the boundary of the country. So the boundary is the spatial attribute. That is the kind of like semantically, it is the spatial attribute that we are going to store, and the ID of the boundary is B1, B2, and so on and so forth. And this ID of the boundary is to help us to link to the boundary table. Alright, link to the boundary table over here. So inside the boundary table, we can see that we have the ID of the boundary, and which serves as the primary key to link to the ID boundary in the country table. And the boundary the table, instead of directly store the actual coordinates, it links to the ID of the contour. The ID of the contour. For example, like the B1 means the Germany boundary, and then it has one contour, and then B2 means France, and France has the two contours over here, which are C2 and C3. And then by having this table, we can know that the countries, these different countries can link to different contours. So the ID of the contour is used in the contour table, and as you can see in the contour table, we have the ID of the contour, and then the number, the order, and also, or you can say the number of the points. For example, the first point in the C2 contour, the second point in the C2 contour, and so on and so forth. And then so this point number will also attach to the ID of the point. The ID of the points, which are the P1, P2, P3, P4 indicated over here in the contour table. So finally, this ID point can link to the point table, which contains the ID of the point and also the x and y coordinates of that point. Okay, so in this case, we can use as you can see, we use just purely the tables in the relational, in the relational database management system to handle the geospatial data. By using this type of the solution, we can also directly benefit from the standard-based SQL query to query geospatial data as well. Okay, but however, this type of solution, it has some drawbacks. For example, like if we want to find the contours of the fronts, then in this case, we can use the select from where and to find out the contours, the coordinates of the contours. So when we are selecting, we select the boundary ID contour and also the x and y coordinates. And from the tables that we just shown earlier, the country, boundary, contour, and points, and where means the condition. The condition is the name equals to France, and then followed by 3 lines of joins. These 3 lines are joins. So we first use the ID boundary in the country table to join with the boundary primary key, and we use the ID contour in the primary boundary table to link to the contour, the contours by its ID, and then by having the contours ID points, the points for that contour, then we can link to the specific point in the point table. And everything can be ordered by the number of the points in the you can say in the contour table. So in this case, as we can see, in order to answer this simple question, find the contours of France, then we need to join so many tables. So the problem over here first is not enough abstraction. So we need to handle the geometries one by one, from the polygon to the polyline to the points. So not enough abstraction makes the management more, you can say, troublesome. The second drawback is the bad performance. As you can see, we need to join multiple tables to answer this query. So, and we already know that the database join operation is a very time-consuming operation. So, so that's another drawback. And the third one is that it's difficult to support new geospatial data types. So other than the, like you can say, by using the points to form the contour, the line, and also by using the line to form the polygon. And it's not so easy to support new spatial data types by using the RDBMS solution. And finally, this type of you can say data model is impossible or relatively impossible relatively difficult to support some geospatial operations. So that's why by using RDBMS to manage geospatial data is not so common. And the second way to support the spatial database management system is the loosely coupled solution. So inside the system, the user, inside the system, we have the DB, the database, and also the files. So the database is used to support the RDBMS, the Relational Database Management System, and the files they are used to support the spatial data management. And the application handles the integration of these two, you can say, data management solutions. The general data is managed in the RDBMS. The geospatial data is managed in the spatial data management system. And then the application can combine the information from these two and then to answer it back to the user. But however, this type of loosely coupled spatial database management systems has some drawbacks as well. So first of all, you need to have two data models. And the one for the general types of data, and the other one is for the geospatial data. So these makes the management, for example, like the modeling of the data, usage of the data, and also integration of the data difficult. So that's the first drawback. The second drawback is you would lose some DBMS features because we manage the geospatial data in the separate in a separate system, like kind of like standalone. Then in this case, some traditional DBMS features it doesn't really benefit from it. That includes the error recovery and also data and also the query optimization, etc. So that's some problems to the loosely coupled spatial database management system. And then in terms of the integrated spatial database management system, which means that the spatial is built in and also it could be extended. So, which means that in the DBMS, the spatial DBMS directly supports some spatial data types and also some operations. And so, you can directly use the extended SQL to manipulate those geospatial data by using the geospatial data types and also the operations. And the spatial query optimization, because we have directly includes the spatial data into the system, so the query optimization can be applied to those geospatial data as well. Okay, so in this case, as you can see, these type of integrated spatial database management system, it has more benefits than the drawbacks, and then because of that, most of the current spatial database management system is following these integrated spatial database. So here are just some of the examples for your information. So here, in general, finally, the requirements for spatial database management system. First of all, we need to support a logical data model for the spatial data. And so, for example, like the point, line, polygon, geometries, those are the data types or data model that we should support so that when users model the spatial database, then in this case, they can directly use the logical data model to describe the data that they want to manage in the spatial database management system. So it allows more data independence and also more abstraction. And the query language, they are usually extended to support spatial operations, like the spatial queries that we have seen before earlier. So like the point query, the window query, those things. And then the spatial database management system, they should be efficient in the spatial data access. So basically, that means the traditional like one-dimensional indexing structure, they are no longer suitable to manage the multi-dimensional geospatial data. So we need some spatial treatment to make the spatial data access more efficient. So that's basically are the different types of spatial database management system. Hopefully, through this discussion, you can know that although there are multiple ways to achieve the management of spatial data in the like traditional database management systems, but however, by using a spatial database management system, the integrated solution is is usually more you can say efficient, and also it's it's easier to maintain for the long run. So that's the reason that most of the existing tools they are using the integrated solution.